Good morning, good afternoon, good evening, whenever it may be. For me, in case you're interested, it's a Saturday morning and I'm in my classroom doing math videos. That's all right because I love doing these. Today we do section 4.4. It's the derivatives of the exponentials and logarithms. Normally in this, I would prove all of these to you, but I know you probably don't want to watch a video of me proving things. If I was in class, I'd probably walk you through these a little bit better. Plus, you may have already seen them. Some of them are proved by the definition, actually. Some of them are just proved using other ones, and some of them are proved using just log rules. But I'm just going to give you the formulas, have you remember them, and then we'll do some example problems, okay? So the first new derivative is the derivative of e to the x. I would probably, in class again, ask if you know any of these. So maybe take a second, pause the video, see if you know these, just a quick review. But the derivative of e to the x turns out to be e to the x. It's a pretty easy little proof. I'm looking at it right over here. Actually, it's using the definition of derivative. So the derivative of e to the x turns out to be e to the x. And I'm not going to do the chain rule here in just a second with these. You can take the derivative of e as a special number, right? E is 2.71. But the next one is just y equals a to the x, where it's any constant, okay? And this turns out to be a to the x, just like it was e to the x, but then we have to multiply it by a natural log of a. This one actually up here actually has a natural log of e in it, but remember the natural log of e is 1, so we just don't write it. So really the e to the x rule, we don't need it because we have the, get rid of that, because we have the a to the x rule kind of supersedes it, okay? The derivative of natural log of x is 1 over x, and we'll do some chain rule problems here in just a second also. You can prove that using some logarithm rules. And then natural log, remember, just in case you forgot, is really log base e, okay? Remember, log is just log base 10. That 10's left off there, right? So there's really a 10 there. So now the last one is just the general one, log any base. This is also 1 over x. Doesn't change, but then we just need that natural log of a again down there. So really there's a natural log of e hiding in that top one also. So there's these for today, plus logarithmic differentiation, which we'll do in a second. So I'll just do some example problems, throw in some chain rules. The nice thing is now you can start to combine all these things. Nice for me. I don't know about you. You can combine logarithm rules with inverse trig functions with quotient rules, power rules with chain rules with logarithmic rules. So there's all kinds of things you can do. So here are just two examples of a combination of these. So this one right here, I see a product, okay? It's 3 to the x times 2x minus 1. So we're going to do a product rule. It's the derivative of the first term, which is 3 to the x with that ln 3 there, times the second term, okay? Plus the derivative of the second term, which is 2, times the first term, which is 3 to the x. Pretty simple, straightforward product rule. We'll do a chain rule on the next one. But that's how that looks with the rules combined. Okay, again, don't simplify it, just leave it the way it is. So now I look at this one, a little bit more complicated. We got a whole bunch of chain rules going on. So the first thing that I see is that thing inside the orange to the second power. So that's a chain rule. So we're going to drop that power. So it's 2 times log base 5 of 3x squared. That's my box, remember. All of that to the first power. I normally wouldn't write that there, but I just want to put that there so you can see it. So let me just rewrite it. 2 log base 5 of 3x squared. Okay. Now I have to multiply it by the chain rules, the derivative of what's inside of the derivative of that box. So now inside this box, let me change the colors here for you. Remember, inside the box is log base 5 of 3x squared, right? So there's another chain rule here. So it's really log base 5 of that box. So the derivative of log base 5 of that box is 1 over that box. Okay. And then we need that natural log of the base down there in the bottom, which is natural log of 5. So that was the derivative of the log base 5 of the box. Now I've taken the derivative of the box. One more chain rule, and that's 6x. It's about as complicated as they would probably get. 3 steps, maybe a couple chain rules. It's just 4 new rules. Really, the rules themselves are pretty straightforward, right? There are the rules, just kind of memorize them. But then you have to be able to apply these rules within all the other rules, chain rules, power rules, product rules, quotient rules, that sort of thing. So you'll see a lot of review. And the nice thing about this is it brings up some review in the other sections. So I'm going to come back here to this. Bear with me one second. I'm just going to kind of hide that. I'm going to tell you there's 4 different types of things that look like power rules. So you've seen x squared. The derivative of x squared is 2x. You've seen 2 to the x. The derivative of 2 to the x is 2 to the x down 2. They look very much the same, but they're not, because the variable's in one place and the constant's in the other place. Don't do this when I go x times 2 to the x minus 1, because that's not the power rule. The power rule is a number to a power. X to a power, right? This is the other way around. This is a number to the x. So gotta be really careful with that. So there's basically 4 different types, right? So the first type is this one, which is the power rule, right? X to the a. So that is a power rule. And that just turns out to be a times x to the a minus 1. Typically we use n, but I'm using a to be consistent with the other one. This one is an exponential rule. Looks the same, but you just got to be really careful with the word is, the exponential rule. So the derivative of this is a to the x times that ln a. This one is a constant to a constant, right? Constant to a constant. So this is just some number. This can fool people. Don't do a power rule. Don't do that. This is just 0. Okay, this is just 0. And then we got this fourth one we have to deal with. This doesn't meet any of those other requirements, right? It's some function of x is some function of x. So I'd like to rewrite these actually as constant, just so you can see it, to a function. This one is function to a constant. This one is function to a function. And then the last one is constant to a constant. Just kind of think about them that way. Okay, so we have to deal with this last one. It's the function to the function. Come back up here. We have a method for this. It's actually called logarithmic differentiation. So the only way to do these problems, don't do power rules, don't do those exponential rules. They don't work. So they're anything that's some function of x to the power of some function of x. Either one of these meets those same requirements. And I'm going to walk you through one of them. I'll do the second one just since it's a little bit harder, but so you can see it all in action. So I'm going to come down here and we're going to rewrite that. Y equals, let me find it again, sorry, sine x to the 3x. So anytime you see a power to a power, actually you could do this for any time you see power. You don't really want to do it for the other ones because we have nice little rules, but this method I'm about to show you works for the power rule also. It'd be a waste of time. It also works for the exponential rules, but you have memorized formulas for those, so it's a lot easier. So the process is, the issue here is these don't meet any of my rules. Okay, it's not a power rule. It's not an exponential rule. So I have to do something else. I'm going to take the natural log of both sides. Hence why it's called logarithmic differentiation. Okay, the reason I'm taking the natural log of both sides is because now I can apply the rule for logarithms that says I can take that power and move it down there. You may remember that, hopefully, that the natural log of x to the y is the same thing as y times the natural log of x. Pretty important logarithmic rule. I'm going to give you 2 other logarithmic rules because they could come up. Natural log of a times b is equal to the natural log of a plus the natural log of b, and then the natural log of a divided by b is equal to the natural log of a minus the natural log of b. Hopefully you remember those. All 3 of those together are pretty important. So the reason I did this is so I can drop that power, 3x times the natural log of sine x. So now I can take the derivative implicitly because I got a y in there, but I just have a product rule on the right-hand side now, right? So it's really simple because that product rule is not exponential. I don't have to deal with it. So the derivative of ln y, be careful here, this is implicit. Derivative of natural log of something is 1 over that something, so it's 1 over y. But then because of the chain rule, I got to multiply it by y prime, or because of the implicit. Now these are product rule on this side. So the first is 3 times the second, which is the natural log of sine x, plus the derivative of the second. I'm going to erase this over here. Sorry, it's in my way. The derivative of the second is the natural log. Be careful here. It's the natural log of box, the natural log of sine x. That's 1 over that box, sine x, times what's inside that box, which is the cosine x. So that's the chain rule for that, times that first term, which is 3x. And then I'm trying to find y prime. So my last step is to multiply by y. So I'm going to get y prime equals 3 times the natural log of sine x. Oops. I'll do that here. Plus 1 over sine x times, again, don't simplify any of this. There's no reason to. And it's going to be all of this times y. The catch is we know what y is. So you can't just leave that y over there. We go all the way back to the beginning. Y is up here. So I'm going to multiply this by y because I'm solving for y prime. But my y is sine x to the 3x. So that's called logarithmic differentiation. It's the only way to deal with a function to a function. It will always work for any kind of, believe it or not, any kind of power rule if you wanted to. But again, because then you just drop the power and do the same process every time. It's good practice, but you have memorized rules for those, so probably not. We're doing it. So that's the exponentials and logs. That's the end of chapter 4. Let me know if you need help. We'll do some review the next time I see you in class.